Hey physics students, I'm going to do this acceleration worksheet 1, so you have an answer key to check your work off of. I got a graph below that shows position versus time of a cart rolling up a hill. So you might consider just for a minute how this graph looks different from your ice puck, which was like not rolling but gliding down a ramp. That graph looked like your position time looked like this. So how are they different? Well, this one's starting kind of flat and bending upwards, and this one's starting with some slope here and bending downward. And this, we know that the puck was starting just from rest with a velocity of 0 and then getting faster. And if you have something that's a cart that's rolling up a hill, it's going to have to start with some kind of speed, and then as it rolls up the hill, it's going to slow down. So we want to think about the slope of this position versus time graph, the slope of this to be how fast it's going. Up here, when it gets flatter and flatter, that's the cart slowing down to a stop. All right, so verbal description of the cart's motion. The starts with some speed greater than 0 and then slows down, and it looks like it peaks at 4 meters. And the peak, the velocity is going to be 0 up at the peak, right? Peaks at 4 meters. And it looks like that happens at time 2.5 seconds. All right. Sketch a motion map of a cart. Well, let's see. I can just read, if I wanted to make my motion map like every... So we have 4 meters, so I make my little line here and have 1, 2, 3, 4 meters. And then I'll make my little dots at every half a second. So I can just read this information out of the graph. At time 0, my first dot should be at position 0, 0, 0. Then at time 0.5, it looks like I'm at position somewhere between 1.5 and 2. So there would be 1.5 and 2, so probably about there. Doesn't have to be perfect. And then the next little tick of time, it looks like I'm at position 3. And then I'm at position in between 3.5 and 4. And then I'm really close to 4. And then I'm like at 4. Right, so if we want to make those arrows, go halfway to the next dot. And you can see the length of those arrows is the velocity. It's a visual representation of how steep this is and how fast that cart's going. Is the velocity constant? No. And there's different things you could say here. Slope of V versus T is decreasing. That's one way you could say it. Other things you could say that would be correct there. Excuse me. If the velocity is not constant, then is the cart speeding up or slowing down? Slowing. And again, kind of the same thing here. Steepness of V versus T is decreasing. Explain how you can tell from the position versus time graph when the cart comes to a stop. different things you could say here, but I think you want to refer to that position versus time graph flattening out. Position versus time is at its peak. If you let this cart go, then if there was nothing to stop it at the top, then it would roll up and then it would roll back down again. And it would look just like this, but in reverse like that. Something like that. Okay, good. Second page. Suppose a cart is given an initial push toward the bottom of the ramp. So it's not starting, it's not just being released like your dry ice puck was. It's got a little push at the start. And then is allowed to travel down the ramp. Assume this is one-dimensional motion where the x, so it's just going this way. That's all that means. Give a verbal description of the cart's motion down the ramp after it is pushed. So it starts with some velocity greater than 0 down the ramp, and then speeds up. As it travels down the ramp. How about the motion map? Let's see. So we can make a little line here. I don't have any scale on this or a graph like I did in this one, so I don't have any like actual numbers to pull out. I just have to make what we would call a qualitative motion map, meaning I don't have numbers to refer to, but I can get like the basic idea of the pattern across here. So it's going to start with the dots like kind of closer together, and then they're going to get further apart as it speeds up. But they don't start super, super close together because it does have that initial push down. So it's going to have like some little starting, that little arrow there represents that initial push, how fast it's going right at the start. And then the arrows are going to get bigger, and the dots are going to get spaced further apart, because every little tick of time that goes by, the cart's going to cover more distance, because it's speeding up. Something like that. Sketch a qualitative, so that means like I don't know any numbers, just want to get the basic shape of it. Graphical representation of x versus t. Well, this is very similar to your dry ice puck, which looked like this, with the exception that here the dry ice puck was released from rest. There was that little ribbon there holding it there, and that got cut. And this cart here is given an initial push, so it's like got a head start. So it's kind of like we're starting from here. So it's already got a little bit of steepness at the very start, which represents it's already having that little initial push down the ramp. So we want the same kind of like bending upward graph that we saw with the puck. We just want it to have a little bit of a head start with the slope here. So the things that we want to be included to make this qualitatively correct are that starting slope that's not 0, and then bending upward. And then how about a qualitative graphical representation of V versus T? Well, when you did that for the dry ice puck, you should have got a graph with a velocity that started at 0 and then got faster and faster. Now, this is a graph of the slopes of this. The slope of this starts at 0, and then they get steeper and steeper and steeper. And the kind of acceleration that we're going to be studying this whole unit is constant acceleration, which means the velocity is changing at a constant rate, which means all of our V versus T graphs are going to be straight lines. These will be curves. These will be straight lines. So what is my V versus T? Is it exactly the same as the dry ice puck? No, because this one starts with a velocity. It starts with that little downward push So it doesn't start at 0, it starts with a little head start, that push. And you could think of, I'm graphing like the slope of this. The slope of this is some small positive number, and then it gets steeper. This position versus time, when we have acceleration, is going to be a curve, and velocity versus time is going to be a straight line.